Hello, welcome to the video. And until now, we looked at typical opamp datasheet and the specifications mentioned in the datasheet. So we'll deep dive more into those specifications, and let's start with offset voltage VOS. And generally, our idea was of comparing the two inputs, taking the difference and integrating it to the desired output. So now what happens is, in reality, there is a random quantity which is an error VOS while taking the difference between the inputs, and that VOS gets added over here, and it can be realized as the voltage source in the series with input voltage. It can be in series with the positive end or the negative end, doesn't matter. So basically what op-amp compares is V1 minus V2 plus VOS and not V1 minus V1 minus V2. So at steady state, we said that we will get V1 minus V2 equals to 0 or V1 equals to V2, but now due to VOS, our V1 is not equals to V2, which leads to error, and those errors can occur in the circuits. So ideally, V0 versus VE should have been a straight line passing through the origin, and the slope is given by A0. So we say that if there is no difference in the two inputs, VE equals to 0, then RV output is 0. So basically something coming from the feedback and something which we are giving as input. So these two should not have a difference when EV equals to 0, and thus we have our desired output. So now as V1 is not equals to V2, so due to this VOS, then we clearly see that when V equals to 0, the output will not be equal to 0. And so in reality, V0 versus VE will look like something like this, and it will not pass through the origin. And when VE equals to minus VOS, the input ends of the op-amp will be having the 0 difference, and thus the V0 will be 0, but not when V equals to 0, but when V equals to minus VOS. And sometimes the gain A0, which is basically a DC gain, can be extremely large, and thus our slope might look like this. And we can say that a very small shift in the ideal curve of V0 versus VE, due to non-ideality, it can shift, and the very small shift can take the op-amp to the saturation when the input is 0. So what will happen basically? So when the input is 0, meaning V equals to minus VOS, then at that point our op-amp can be at saturation. And ideally, it looks like we can use op-amp in open loop, but we cannot use op-amp in open loop. And as V equals to 0, op-amp is in non-saturated region when we are seeing ideal case. But in reality, due to VOS, we always need to use op-amp in negative feedback loop. And here is how we have showed that. And now, what does this offset voltage do to our amplifiers? So let's take a non-inverting amplifier with a feedback gain K, and we have our VOS in series with the input. So for simplicity, assume that DC gain is infinity, meaning when we reach a steady state, the positive and the negative inputs of the op-amp are virtually shorted and identical to each other. So this means that voltage at positive end, which is, sorry, voltage at negative end, which is V0 by K, also appears at the positive end. So we know that at positive end, we have a voltage of Vi plus VOS, and which is nothing but VOK due to the virtual short. So we can write this equation, and from this equation, we see that V0 is not K times Vi, but it is also K times VOS. This means when input is 0, the V0 is not 0, but K times VOS. And depending on the circuit we build, the gain from the input to output for VOS and Vi might differ. In this case, it is K times Vi and K times VOS, but not necessary for every circuit. So let's take another circuit. Let's take inverting amplifier. And in this case, again, assume infinite DC gain, thus virtual short is there. And now voltage at the negative terminal is nothing but Vi times K minus 1 divided by K, which is due to this divider, plus V naught times 1 by K. So this is the voltage at the negative terminal, and we know that at both the terminals same voltage will lie, and at the positive terminal there is VOS, so which is equals to VOS. So same voltage will appear at this end, which is equalized to VOS. So we get this equation from this, and after solving this, we will get V naught equals to minus of K minus 1 Vi plus of K times VOS. So this is our desired output, but at the same time, when Vi is 0, output will not be equal to 0, but it will be K times VOS. And we said that it's not necessary that the gain should be same for Vi and VOS. So this is the case. Now, coming to the another factor which is given in the datasheet, which is common mode gain or common mode rejection ratio. So this is something related to a op-amp. When we take two terminals and we give the input, so basically we expect that let's take two terminals as Vi positive terminal and Vi M is Vi minus terminal. So we expect that the output should only respond to Vi minus Vm. So the whatever the output comes, it should only respond to these inputs, meaning it should only look at the difference in the inputs. But due to limitations of circuits with which the op-amp is built, it turns out that the op-amp also responds to the average value of VIP and VIM, and ideally at DC, V naught equals to A naught time VIP minus VIM. This is what we expected over here, but in reality, V naught is A naught times the difference plus this is the common mode gain times the average of two inputs. And this is what a common mode rejection ratio is. And when we say that the ACM, which is common mode gain, should ideally be 0, but in reality, even though it will be much smaller than A naught, but still it is a non-zero value and we should consider it. And to figure out how small it is from A naught, we can specify the value of ACM while designing. But usually we specify the ratio of A naught by ACM in decibels. For example, 20 log A naught by ACM. And this is the ratio is called common mode rejection ratio. And it is also a part of datasheet. So effect of non-zero common mode gain, which is ACM on our circuit is, uh, first of all, let's take a non-inverting op-amp in a negative feedback. Now we can't just consider difference voltage or input, but also we have to consider the average of these inputs, VIP and VIM. So our V naught will be like this, as we said earlier. But we also know that our VIM means at our minus terminal we have V naught by K, and at our positive terminal we have Vi. So putting these values in this equation, we see this kind of equation. And instead of solving it properly intuitively, let's assume that the differential gain A naught is very large, and initially the common mode gain is 0. So this is the same situation like earlier, which we have been deriving till now. So VIM is VIP is equals to VI due to the virtual short condition, and thus VIM is equals to V naught by K, and which is equals to VI, and therefore we can say V naught equals to Vi times K, and this is the ideal case. We have discussed this. Now say that the common mode gain has small value but not non-significant value, and thus output will not change significantly. So so the VIM will not change significantly, but due to virtual short, VIM is equals to VIP, and VIM plus VIP by 2 will become Vi by 2, or let's say Vi plus Vi divided by 2, which is 2 Vi divided by 2, which is Vi. So as VIM becomes VIP, and we know that VIP is Vi, so from here the average becomes Vi. And now because of the common mode gain, the output has some change, which is, let's say, delta V. So delta V will be ACM times Vi, and thus the output will look like K times Vi plus ACM times Vi. And in this case, the gain is K plus ACM instead of K. The value of ACM is uncertain, which causes a small error. And although we represented the transfer of common mode voltage to output as linear function in reality, so like over here, we represented the transfer function of common mode voltage to output as linear function, but in reality, it is some non-linear function of the common mode voltage. And we have mentioned over here that V naught is something K times Vi plus ACM times Vi. So error here is non-linearly related to Vi, and this causes some kind of minimal error in our inverting op-amp configuration. So non-inverting op-amp configuration. So now let's take an inverting configuration in which we will calculate the inputs of the op-amp assuming there is no common mode gain, and use that common mode voltage to calculate the error due to the common mode gain. So we assume that the DC gain is infinity, and thus there is a virtual short between the inputs, and VIM equals to VIP equals to ground, which is 0. So common voltage is nearly about equal to 0, and thus our V naught is nothing but minus K minus 1 times Vi plus ACM times the common mode voltage, which is nearly equal to 0, and the error due to ACM is non-linear. So this brings out one of the key differences between inverting and non-inverting configurations. So when it comes to choosing one of them, we look at the performance metrics. For example, non-inverting configuration provides infinite input resistance, whereas inverting has input resistance of R. But the main thing over here is um, the difference between two based on the common mode performance. So we have large common mode voltage in non-inverting case. The effect of non-linearity will come out strongly. But in inverting configuration, the common mode voltage is almost 0. So effects due to the common mode will be very, very small. And sometimes in sensitive cases, which are sensitive to distortion, we tend to use the inverting configuration, as the effect due to common mode will be very small. So now we will discuss another type of amplifier. So that amplifier is called transimpedance amplifier, and so basically we know what is a photodiode. So a photodiode is basically something which produces a current after light shines on it, and there is a diode in reverse bias, and the current flows through it after the light falls. So we have a diode in reverse bias, and the current flows through it when the light falls on it, and it is represented as a current source in parallel with a fixed capacitance CD, and it always comes with a large capacitance in parallel. So we have our photodiode, and this is our current source. So to take a voltage from it, initially what we'll do is we'll attach a R in shunt, and we will take the voltage across it, which will be basically V naught equals to, let's say it produces a current IS. So the voltage across the R will be IS times 1 upon total impedance, which is 1 upon SCD plus 1 by R. So basically the V naught will be IS times R divided by 1 plus SCD R, and from this our DC transimpedance comes out to be just R, and our pole, let's say, lies at 1 upon RCD. So our bandwidth will be from 0 from origin to our first pole, which is 1 by CD R. So here CD is fixed and cannot be reduced. So for a given bandwidth, R is fixed. R, like the gain is fixed. So if we want to fix the gain, or we don't want to compromise with the gain, then we can't do anything with the bandwidth. Or in another case, so the bandwidth is basically 1 upon CDR, and if we want higher bandwidth, then if we want higher bandwidth, then CD is already fixed. So we have to reduce the value of R, and over here we have seen that the DC gain is R. So we need to reduce R, and in order to increase the bandwidth, we need to compromise the DC gain. So let's solve this issue using a current controlled voltage source. So now what we have is we have our photodiode and we'll use a current controlled voltage source. So from here we know that at this point our transfer function from this point to this point is, or the voltage at this point is basically V minus V naught S times omega U, as this transfer function of this op amp is omega U by S. So what will happen? There is this current and there is this current. So basically this current is equals to V naught by R plus V naught by R plus V naught S by, means this voltage, divided by R. So total voltage is this voltage minus this voltage divided by R, and due to the minus sign we have V naught 1 plus S by U divided by R, and this voltage is this current is nothing but this voltage divided by the impedance due to CD, which is V naught S by omega U, this voltage divided by, multiplied by SCD. So now the total current is the sum of these two currents. So we will take the sum of these two currents, and from this equation we will get the equation in terms of IS and V naught. And we know we had input as IS and output as V naught. So V naught by IS from this equations comes out to be this, and this is our transfer function. And when we compare this with the standard form, so we get the quality factor, and we know that the quality factor is 1 upon 2 sigma, where this is the 2 sigma. So while comparing it with the standard equation, our natural frequency comes out to be root of omega u by CDR, and our sigma value comes out to be half of root of 1 by omega u CDR. And now let's say we want sigma of 1 by root 2, considering the damping and ringing. So if we want our sigma to 1 by root 2, so we can equate this value to 1 by root 2, and then our omega u basically comes out to be 1 upon 2 CDR. And thus, whenever sigma is 1 by root 2, the bandwidth is always equals to the natural frequency of the circuit or the equation. So we can achieve high omega n by making high omega u, but then this reduces the damping factor by the unexpected level. So again, while increasing the bandwidth, we again face the error, which is that initially we faced that we have to compromise with the DC gain, and now when we are using current control voltage source, we are expecting we are getting a reduced damping factor, and due to this we are getting unexpected level of ringing, let's say. So let's examine the loop gain over here. So what we'll do is ground the input and break the voltage from here. So now we can say that from here to here, the transfer function is 1 upon SCD divided by R plus 1 upon SCD. So basically 1 upon 1 plus SCDR. And when we plot this as a Bode plot, so this is our transfer function, and this is where our pole lies, which is 1 upon CDR, and this is the curve for the loop gain. Now let's say we take an amplifier with omega u by S and attach it. So now for that amplifier, the curve will look something like this, and we club these two curves, this one and this curve. So basically we will be getting a minus 20 dB roll off, and when the pole occurs, we'll be getting minus 40 dB roll off. Now at omega u, the behavior is not minus 20 dB, but it is minus 40 dB. And from this curve, it clearly shows that this circuit is unstable. So we need to take the value of omega u lesser than the first pole, or let's say lesser than 1 upon CDR. So let's choose a smaller value. So now if we choose a smaller value of omega u, which is before 1 upon CDR, so then the curve will look something like this, and when the pole occurs, it will start by minus 40 dB roll off. And now we can see that it is stable, and given the value of CD and R, we can not choose omega u to be higher than 1 upon CDR. So basically, to make omega u higher, we can introduce a 0, which will give us a phase lead. So I think this is the solution to the for increasing the bandwidth, as we also need a higher bandwidth along with higher gain, and we are facing issues while increasing the bandwidth. So now let's say this is the case, and over here also we cannot increase our omega u beyond 1 upon CDR. But for that, what if we introduce a 0? So if we introduce a 0, it will provide us a phase lead. Now from the output of op-amp to the input, we have first order system. So from here to the input, we have first order system with R and CD, the R and the CD, and the transfer function is 1 upon 1 plus SCDR. Now if we add a 0, let's say we add a 0 by adding a capacitor in shunt to R, the transfer function will become 1 plus SCFR divided by 1 plus S CD plus CF times R. And in frequency domain, it means that the 0 will provide a phase lead, or let's say the R takes a long time to charge CD, but now we provide a lot of charge by connecting CF across it, or let's say CF provides a faster path than R, so the path from R is slower path. So these things we can estimate from adding a 0. So basically what happens is this is our circuit, and at this point we have a voltage of minus V0 S by omega u, and now we have this current and this current, and these two in addition makes IS. So we write the equation for it, and when we write the equation for IS by adding two currents, we get the transfer function as this big equation. And if we make CF equals to 0, then our V0 by IS transfer function looks like this, and which is a sanity check before, because when there was no CF, again when there was no CF, our transfer function looked like this. So this is how we check this sanity. And after we done the sanity check, so now we can compare this equation with our standard equation and find the values of sigma and omega n, which comes out to be these values. And then we consider a case where we need our sigma to be 1 by root 2, and when we compare this and square both sides, so we can get this kind of equation, from where we can say that our CF times R square is equals to 2 CDR minus 1 times omega u. And from this equation, from here, for given value of omega u, we can choose the value of CF for the sigma to be 1 by root 2. Now it is possible to use op-amp with higher omega u and increase the bandwidth, but the condition for this to happen is, for the condition for this to happen is, we need to introduce a 0 with introducing a CF in shunt and adjust the value of CF according to this equation. So now what will happen? So basically we will using this circuit, we have a transfer function of this, and when we will break the circuit from here, so we will get a transfer function of our loop gain, and it will look like something like this. And now when we choose a higher value of omega, let's say our curve is looking like this, and when we choose a higher value of omega, so what will happen is we have a curve like this for our op-amp, and when we combine the curve, so at our first pole and at our first 0, so here, even though it drops by minus 40 dB roll off, but due to the 0, it will again rise by minus 20, and it will give a first order behavior near our omega u. And let's say that due to this reason, thus given with a higher omega u, the circuit is stable when put in a negative feedback loop. And this technique is also useful when we have inverting op-amp configuration. Basically, this is our inverting op-amp configuration where we have R times Vi, and due to this thing, there is always a parasitic capacitance between this node and ground. So this, let's say this is our parasitic capacitor, and this R times Vi. So if we reduce or redraw this combination of combination to Norton equivalent, so we can represent it as a current source, which whose value is Vi upon R1, and then there is a parasitic capacitor. And in this case also, by putting CF across R2, we can reduce the effect of instability because of the parasitic capacitance. So I think that's all for today's video. Thank you for watching.